In this section, we're going to be looking at Pythagoras' theorem. As a first step, consider constructing triangles. If you construct a triangle with lengths 3 centimeters, 4 centimeters, and 5 centimeters, when you measure this angle, you'll find that it's a right angle. 3 squared plus 4 squared is 5 squared. This is 9 plus 16 is 25. This happens in a right-angled triangle and leads us to Pythagoras' theorem. The longest side of a right-angled triangle is known as the hypotenuse. What we found with the 3, 4, 5 triangle occurs provided a triangle is right-angled. If we have a triangle, the hypotenuse is of length A, and the shorter sides are B and C, then A squared, the length of the hypotenuse squared, is equal to B squared plus C squared, the lengths of the two shorter sides, squared and added. The question arises as to how Pythagoras knew this. In Greece, they used many elaborate tiled patterns on the floors. It's thought that he may have spotted a right-angled triangle between 3 squares. Let's just shade those shapes to make this clear. Here we have our right-angled triangle with lengths A, B and C. Note that A is the length of the hypotenuse. The area for this square would be A squared, the area for this square would be B squared, and the area for this square would be C squared. All that's then required is that you spot that the area for this square is equal to the area for this square added to the area for this square. You may ask, was it his idea? It's called Pythagoras' theorem, which suggests that it was his idea. However, Pythagoras worked with a very large group of mathematicians who were essentially his research students. It's possible that one of them actually had the idea. An interesting thing about Pythagoras, which has nothing whatsoever to do with mathematics, is that he had an irrational fear of beans. This actually led to his death. Apparently, whilst being chased, his only path of escape was across a bean field. Rather than enter the bean field, he stopped and was killed. Another question you may ask is, does it only work for right-angled triangles? Let's consider this model. We have a triangle here, and on the sides are 3 squares. Over here we have the angle, which is this angle just here. We're going to adjust this angle. Here we have the sum for the green square and the black square, and here we have the area of the red square. We can see that these are not equal at the moment. We know from Pythagoras' theorem that when this angle is 90 degrees, these areas should be equal. The question we're asking is, are they going to be equal anywhere else? Let's start changing the angle. If we change this angle, you can see we're now down to 122 degrees. The areas are still not equal. Let's keep changing Note this one stays the same all the time. That's because I've fixed the length of these two sides. So really we're looking for when this one gets to 25. It's getting closer to 25. You can see the value is going down. The area of the red square is reducing. We're now at 91 degrees. At 90 degrees it becomes equal to 25. This is Pythagoras' theorem. The area of this square is equal to the area of these two squares. As soon as we reduce below 90, the red area is less than 25. So it only happens when the angle is 90 degrees, and therefore Pythagoras' theorem only applies in right-angled triangles. So, if the triangle is right-angled, that means that a squared equals b squared plus c squared. A right-angled triangle means Pythagoras' theorem applies. If Pythagoras' theorem applies, the triangle must be right-angled. So Pythagoras' theorem works both ways. It works if the triangle is right-angled, and if it works, the triangle must be right-angled.